Our next speaker today is Pascal van Putten. Pascal is CEO of VPInstruments and has 20 years of experience. I will now turn it over to Pascal.
Thank you, Kimberly. It was, by the way, a very nice presentation from Tim. Really inspiring again. And in this part of the webinar, I will discuss the do's and don'ts when it comes down to compressed airflow measurement, and basically the do's and don'ts of using sensors. Because when applying flow meters or any sensor, it's garbage in, garbage out when you don't apply them properly. In other words, yeah, it's an art measurement. And talking about art, people sometimes ask us about our logo and yeah, what it stands for. Well, I created this logo myself when starting the company back in 1999. I used to be a sort of hobby artist doing abstract painting, and just as yeah, with measurement, it's basically also an yeah, measurement is also a form of art. And so the logo stands for creativity in basically solving measurement problems with 2 eyes for detail. And maybe you notice the blue line, which is a measurement signal. And just as with art, and especially with abstract paintings, it's also a matter of sometimes leaving things away or eliminating things and making it more simple. Just like what Tim pointed out, you don't always need a lot of sensors to already create insight in your compressed air system. Now let's look more closely into flow sensor technologies. There are a lot of different technologies out there. There are in fact so many different technologies, and with all their pros and cons, that we have a 1-hour webinar just on this subject, which you can find at the end of this part. I will show you a QR code. You can go to our website and then register for that online course. But it all starts with some basics, and I would like to emphasize today a few of those, and also 2 important ones which are often confused and also of utmost importance when you're doing compressed air audits or compressed air monitoring. So the basic ones are accuracy and precision, and those are often mixed up by people using these terms. So I just want to repeat what it really stands for. So accuracy is how close a measured value is to the true value, so to the true physical value. Like if you have a 100-pound bag, it should really show 100 pounds on your weigh scale and not like 90 pounds. Precision is how close measured values are to each other. So if you do, say, 5 subsequent measurements of that 100 pounds, it should be 100, but it could be maybe 105 and then 95. It's still, in average, your measurements are still 100, but there is some scatter. And it depends on the application what you really need. For example, if you trend leakages, it's okay to have a systematic error, just like what Tim pointed out with his watch. It's okay as long as that error is consistent over time. Then you can still compare where you are and where you want to be over like 6 months and compare those 2 numbers. But if you have a control system, in that case, you want high accuracy of your pressure sensor and also high precision, because you don't want to run your system on like 100 psi and then find out later that your pressure sensor is actually measuring 90. So in that case, you're running either too expensive or you have problems in production. So with those critical applications, you need high accuracy and also high precision. Also, why this precision is important: if your pressure is noisy, your pressure signal, your controller might get a little bit crazy and start to turn off or turn on compressors, which you also don't want. But if you do a long-term audit, like for days or for years, then it's okay to have some noise in your signal. As long as you have an average value, then you can still trend it. One of the biggest enemies of sensors in general is drift. So that's something you don't want. You don't want that the sensor drifts like within a week or a year and then shows a different value, because that really can drive yourself crazy. And drift is in compressed air often caused by pollution of the air, like oil or particles or rust. that can affect the measurement over time. Also, flow range is critical, and I just want to go over two technologies: thermal mass versus differential pressure. Tim also mentioned those two technologies. Differential pressure, by the way, is similar to vortex in that sense. The dynamic range of such sensors, differential and pressure and vortex, is smaller, so you cannot measure leakages and high flows with the same instrument. While thermal mass flow can be used over a very large range, so you have like a sort of one-size-fits-all solution that can measure both leakages and also the nominal consumption of air. Another thing to be aware of is bidirectional flow. Compressed air can go basically two ways. It can go back and forth, especially if you have a lot of receivers in your system, or multiple compressors at different locations along the building. And this is an example I encountered once in the field, where there was a point of use receiver and there was a production machine, and that machine was turned off. And for some reason, the flow meter was showing still a value, sometimes going up and down, up and down. And it appeared to be that the other production lines were basically stealing the air from that little point of use receiver, and it was just going reverse through that flow meter. So that's why we recommend, especially in audits and in bigger systems, to use bidirectional flow sensors, so you can see those reverse flows and get to the right conclusion. Air quality, already mentioned that it can cause drift, and obviously if you have a situation on the right side, then you don't want to stick any sensor in that. You first want to talk to maintenance to clean out that pipe, and maybe also to look into the filters. What we sometimes find in say carbon steel pipes, sometimes that those pipes are a little bit rusty. The air could still be dry, but there could be dust flying out of those pipes and hitting your sensors or fouling the sensors, and that can change the accuracy, or it can cause the sensor to drift. So that's why regular maintenance is then also important, to clean the sensor and get them recalibrated. When using insertable probes, regardless of the brand or type, if it's an insertable probe, it uses the inner pipe diameter and the inner area of the pipe to calculate mass flow. And in that case, it's really important to check if you have really the true inner diameter measured properly. So you can do that, by the way, by using a circumference tape, which you can make yourself, or you can buy one online. And then you use, not too expensive, a ultrasound thickness gauge, where you can measure the pipe wall. And in that way, if you know the wall thickness, you can really very accurately calculate the inner diameter, and in that way also calculate the inner area of the pipe. And you can see here, if you have a small diameter, 2-inch, and you have a 0.12-inch error in your inner pipe diameter, it can already result in 10% error. So be aware of that. One other thing which is really important, is having enough straight pipe, and that's based on physics. So you cannot really beat physics. It's just the way it is. So be aware of it, and make sure that your pipe length is long enough to get a nice symmetric flow profile. And I want to show you one example. Sometimes you have to look a little bit further, maybe look outside to find that straight pipe. So in this case, you see a little picture of the inside, then there's the wall, and on the outside of this wall there was enough sufficient straight pipe run. So in the end, in this project, the flow meters were installed outside to allow the flow profile to become nice and symmetric again. Measurement is an art, and sometimes people are really artists installing flow meters in the wrong way. So here are 3 pictures I want to share with you on how not to install flow meters. First one on the left, you see that the flow meter is very close to an elbow, and there's also a valve, which is a bell valve, and I hope it's full bore, otherwise you have another issue. So this is really not the way to go installing an insertable flow meter. The other one is upside down in the middle, and I also disencourage to do this, because it will be a sort of condensate trap which you created there. So if there's any water inside or dust, it will collect in that ball valve, and it will eventually it might destroy the meter or corrode the meter, and you get a free shower if you take the meter out. The right one, that's a flow meter that someone installed under a big angle in a vertical pipe. Very creative, but not the way to go, because in this case, if you use the triangular formulas, you will see that it will basically show a lot less than it should do. So it's nice to have sometimes a little angle to get the water out of these differential pressure meters, but this is really exaggerated. So don't do this, please. And most of these things you can find, of course, in the user manual that the vendor will supply, and then you can prevent these kind of mishaps. I want to share one more example before I come to an end of my part. Sometimes you have these very complex big projects where the compressors are being monitored on their outlet. It could be centrifugal machines in this case. And also there are flow meters measuring each department. And then you find out that there is a little difference between the sum of all these flow meters on the supply side and the demand side. For example, if you glance at the numbers instantaneously. Now, what could be the reason of this? There could be many reasons. One of them being system latency, because there is a receiver in the middle. It could be just latency where you're looking at. So the compressor might be offloading, or a consumer might use a little bit more air, and then you will see differences. The demand can then be higher than the supply, for example. But if you look at the longer run and you still see this difference, it could also indicate that there is some leakages in air treatment, or there may be a drain that's open, like a timed drain, or an automatic drain that is broken and needs to be cleaned out so it closes nice again. Or it can be one of those flow meters downstream that has an installation error causing this. Now, one trick which I would like to share with you today is how to solve this. And that's basically adding up all those consumers and convert them into percentages of the total sum. So you create the percentage of the total sum of that 12,500. So then you can allocate basically the total flow to each consumer using the sum on the left side, the 14,000. And you can even go one step beyond. You could also use the kW meters if they are installed and allocate kW to the consumers instead of allocate standard cubic feet or standard cubic meters. So there are ways mathematically which you can implement in a monitoring system or in a control system to at least lower the total measurement error in that way. My last slide, some tricks and also basically a basic checklist which you can use. This checklist is really important when you select the flow meter. Always check type of gas. Is it air, or is it nitrogen, or maybe some technical gas? You need to know that. Check the flow range. Check if the air is dry or wet. Check the inner diameter and make sure it's right. And also check the other things like pressure and temperature range, so the flow meter can meet those requirements also. There is a full checklist which you can access through the link here, scanning the QR code, and that also brings you to the more extensive training on flow measurement. So thank you for attending today my part, and now I will hand it over back to Kimberly and to Justin Johnson of FS Curtis.